Hey guys, my name is Ankush Mahajan and this is my project one of computer vision which my topic is previous work on people detection. So this project is all about talking about the algorithm which is presently present and currently they are used in detection of people and objects. And so using this we can tell the people blind people the number of people around them which will help them to understand the surrounding. Okay, so in this tutorial, I'm comparing a total number of 4 algorithms. Yeah, which will be discussing the website tutorial and their strengths and their results and their drawbacks, everything. So, guys, let's just hop to our website. Okay, so this is my website, which is a previous work on people detection. So this website has been divided into 6 parts, which is like introduction, implementations, application, results, conclusion, and references. So in implementations, I have presented all the algorithms which I have researched, and put a data on. So in application, we'll be looking at one of the prototype which has been built by the students of University of Maryland, which is a working prototype. Okay, and so in results, so we will be comparing all the algorithms and their power, their accuracy, their everything. And in conclusion, we'll be just wrapping up all the things which I will discuss in the tutorial. So in the introduction, what is the most important sense for a human being? That's right, it's a vision. We are blessed to have this vision, but there are few people who are not. According to the survey, there are millions of people who are either visually impaired or have lost their vision. So without this vision, the people have difficulties to understand the surroundings. If we imagine, like if we close our eyes and if we try to walk or if we try to interact with something, we'll have a difficulty. So consider about the people who are blind or who can't see properly. So this project is kind of helping them to access the information around the surrounding and helping them to live a better life. This project also focuses on working for making a visual world into an audio world. That is, I mean, when a camera will detect the object, it will be translated into audio object and will be implanted into user. So that will help them to understand the surrounding around them. This application uses image processing, machine learning, and OpenCV to determine people around the person. So there is a video I have posted in the introduction which roughly describes what can be done with this technology. If you have time, you can go through this video. Okay, let's go to the implementation parts. Okay, guys. So this is a basic, rough implementation of what I was working on. Okay, so as per the diagram you can see here, there will be one Android app where you can open the app and you will give permission to camera to access app to access a camera. So when the camera will access, it will try to scan the surrounding around the phone. So right now we have this cute little kitten over here, and so this image has been sent in real time to the server, and then after that there is one box is appeared on the kitten, and that audio voice output will be fed to the user. It will be like, there's a cat up ahead or there's a cat besides you, so what. Okay, so this magic, how this magic happens? There are like algorithms. There are algorithms which are present to make this magic happen. So there are like I've been working on 4 algorithms which are like frame differentiating. Sorry, my voice. Frame difference, CHT, histogram or object gradient, and YOLO. It's not you only live once. It's you only look once. Okay. So let's go on differentiation. Okay, so guys. So if you want to go through all the all the algorithms, I've been put a next button so that you can go to next algorithms. You can go to previous algorithms. And if you think you are ready to, if you understood all the algorithms, you are free to take a quiz. And yeah, guys, if you're taking a quiz, please make sure you check this, okay? Because let's just be honest, okay? I mean, the answer is right over there, but you guys, just try to understand, okay, guys? Okay, let's hop back to our frame differentiating part, okay? So frame differentiating, the name suggests we have to differentiate the frames of an image. So how does this frame differentiation happen? This method extracts pixel wise of a current frame and then to detect the objects, right? So it is popularly known as a temporal differentiation, in which a background model is subtracted from a video frame at the time t minus 1 second. Okay, interframe difference method computes the absolute difference between previous frame and the current frame. Okay, the formula is given by difference is equals to frame t plus 1 minus frame of t, which is the next frame minus the previous frame. This subtraction helps extract the foreground. Okay, so the detection object are identified as human by analyzing the blobs. I mean, we have seen like the cat has got a blob. So this detector of moving objects are be classified like that. And so people counting is performed by bounding box with centroid method. Okay, for each blob, a bounding box is created, and the number of such bounding boxes present over scene at a particular time gives the people count. So if you if when you're scanning something, the blobs will appear. So the algorithm will calculate all the blobs, and then it will show present a number to the user. Okay, and as the discussion is, if you want to know more about it, I have posted a video right over here, which discusses more about frame differentiation. Okay, let's move on to our next algorithm, which is circular Hood transform. Okay, so the name suggests circular transformation. So that's right. This algorithm uses circular blobs to detect a person or objects. So this formula is being given by xi minus a whole square plus yi minus b whole square is equals to r square. R square is equals to radius of the circle which has been formed by circular blob. Okay. The xi yr represent an arbitrary point of interest in the object boundary. A and B represent the center of the circles. Okay, it's not like it will be form only one circle. Okay, this video right over here will showcase the examples of how the circles will form. So there will be two circles. So every circle has its own center. So this circle will sorry, okay, my bad. And the radius of r is the radius of the circle. Okay, so this formula right over here does give us a the length of a radius. Okay, so so the advantage of this is that it can be handled the missing and occluded object. Occluded means sometimes some interference comes in with like lighting, everything. This can handle such kind of informations while using a overhead camera. But the problem is that it has to be implemented only on inclined camera. So if you are like holding on a handheld device, it won't give the result which will be given by inclined camera. So it can be used in the smart glasses, or sometimes it can be used in inclined glasses, but it can't be used on an app. Okay, so if you want to know more about this algorithm, I have posted a video right over here. Okay, so we move on to the next algorithm, which is histogram of oriented gradient space people counting. Okay, it is popularly known as HOG. So HOG is an object detection technique which uses distribution of intensity gradients or edge detection to define the shape of an object. Okay, so this separates all the color and the intensity and try to identify the object based on that gradient intensity. So it uses in both horizontal and vertical directions. So this one right over here minus 101 and minus 101 raised to t are used as filter in the horizontal vertical direction respectively. Okay, so when it is like filter, it is when the features are detected, the humans are classified using a classifier. In this classifier we use a SVM classifier. We use both the linear and non-linear kernel classifiers, which are like the one linear kernel and a non-linear kernel like RBF, radial basis function. Okay, so we move on to the next and the final algorithm, which is called as YOLO, you only look once algorithm. So based on the computational speed, the YOLO version 3, it is the latest, fastest and more accurate than previous version of YOLO. I have presented a table right over here to describe how accurate the YOLO versions are. Okay, so for this table we have the input image is divided into grid cells, and based on the grid cells and we have implemented YOLO algorithm, and then and how many boxes are predicted we have calculated according to that. So for YOLO version 1 we have used 7 by 7 grid. I mean, it can do 7 by 7 grid only, and the boxes are identified by this version is 98. Okay, and with the version of version 2, where the boxes grid cells has been increased by 13 by 13 by 13. It's almost by 6 times the previous version. And of course, as we have increased the grid, the boxes will also be increased, right? So the number is 845 boxes, but the version 3 is the same grid cells, but it the time of boxes is like the boxes count is 10 times the boxes count of your YOLO version 2. Like it's more like 845 into 10, so it's more like 8450 boxes just in 13 by 13. You see, like that's why we have said that is the latest, faster, and more accurate than the previous versions. Okay, so but problem with this algorithm is that this algorithm can be used in web application with a precise rate, but on a phone, the problem is on a phone that we have less computational power when computer web applications. So thus we use a tiny YOLO data set for detection algorithm on an Android application. If you want to know more about the YOLO algorithms, you can take a look at this video which have been posted for more reference. Okay, so we go to the application part. So this is a glass access. Okay, so it's a combination of glasses plus access. It's a pedestrian detection prototype. This is used to help people to access visual information about the people around. Sorry. Okay, the prototype estimate visual attributes of people who pass by the blind people. This model consists of a server and client. This diagram right over here, it gives us a gist of what's the system architecture of the prototype is. So the step 1 is taking an images. For example, if you're wearing glasses, so the camera in the glasses will take an image, and the image will be sent to a server. So backend pedestrian detection models will work on that image to identify the face, the gender and age, and head pose estimation, like if we are looking at the person or not, and distance from the person, which is really good. Okay, and so like for example, we are right here we have given like Amy 0.3 probability, 27 age is 27, and the gender is female, and head pose estimation. As I said, if whether the person is looking at you or not, it will be detected by these glasses. So right here it says that person is looking at you, and the distance between the person and the blind person, which is 2 feet. Okay, so right over here I have been describing server, client, and the feedback message you will be getting. Okay, so server will be processing all the data which has been sent through images, like the name, age, gender, head pose, and distance estimation, everything. The client is all smart glasses which will be containing this app, and which will be doing the simulation in real time and capturing the picture and sending to server in a real time process. Okay, the feedback message, which is the most important part, right? So the client the output of this processing done at the server. So client has two modes, mode A and mode B. Mode A is quantitative feedback mode. It uses foot metric for distance estimation and approximation for age estimation. For example, 2 feet, looking at you, female, 20. And mode B, concise feedback mode. It simply says whether pedestrian is detected to be near or far. Age is estimated as young. Age is less than 35. Okay, so the output will be like near, looking at you, female, young, which is comparatively lesser accurate compared to mode A. So there is implementation right over here which uses all the softwares and how the data has been set, everything. And here right now we have a video where it showcases how the working of this pedestrian detection model. We'll be looking right here. Okay, so see guys, so this output right here is the mode A output, where the person the output is generated as David 36 not looking at you. Okay, so this is how the prototype has been deployed by these students, and which is really good initiative towards the people detection. Okay, so let's go to the result part. I mean the algorithms comparison. Okay, so at first we compare the frame versus the circular Howard transformation versus HOG. So okay, so the algorithm frame difference is like 0.4% accuracy. Okay, so it's like 41% accurate, and the response time is lowest among all the other algorithms, which is 14 seconds. Compared to that, CHT is like 0.6%, 0.6 accuracy, but the response time is like more than 3 times, which is 46 seconds. Histogram oriented gradients. This have been divided into two parts because, as I mentioned in my implementation part, that we will be using both the linear SVM classifier and non-linear classifier. So the linear classifier gives us 74% of accuracy, but the response time is the longest of all, which is 112 seconds, which is more likely 2 minutes. Yeah. So and the second is non-linear one, which is the most accurate one. It's gives us 78% accuracy with a response time of 87 seconds, which is quite large when compared to rest of algorithms. But if you focus on the accuracy part, the non-linear histogram gives us a better result rather than all the frame giving response at a quicker time, but accuracy has been compromised. So right over here we discuss how the HOG high density and frame differencing high density detects. You can see over here in the images that people standing over here are detected as one blob only, but HOG detects every person with accuracy of 78%. It can detect almost all the person in the scene. But okay, now we'll move on to YOLO performance in object detection. So this table has been divided into two parts. We use Tiny and we use YOLO. So for our references, okay. So we so the Tiny and YOLO has been implied on the same image resolution, which is 416 by 416, 608 by 608, and 832 by 32. Okay, the iterations it takes to analyze all the images, all full of images. There is the 42,000 for 416, 21,700 for 608, and 55,200 for 832. And compared to that, version 3 does a little less, which is 19,800, 2,900, and 5,600. And then when we compare to average loss, means not every algorithm is optimal. So there is some losses in detection. So first, when you look at the lowest resolution picture, the average loss is 0.19. So that's 19%. When we increase the resolution, we get a total loss of 34%. And the largest one, we get the loss of 23%. So on the contrary part, YOLO version 3, when we use the low resolution, loss is only 19.45%, which is lesser than version 3 Tiny one. But as we increase the resolution right over here, we can see that the loss is significantly increased by 71 to a 71%, which is a lot over there. So at this stage, the Tiny YOLO version 3 takes the round and says that I'm the best. Okay. So and if you look at the mapping percentage, the compared to all the algorithms we have presented, Tiny mapping is better than that of YOLO version 3. Okay, so we move on to our conclusion part. So what we have learned, guys? The challenges. Okay, so everything will poses a challenge for us. Okay, so for this people detection, the challenges will be camera orientation. So we can give the blind person to hold the camera in his hand or use it in glasses. But every orientation have their own different view angles. So the covering area will be different for every angle orientation. So it must be considered. If okay, so if you if you held in the hand, the angle will be all the one straight forward. If you take a glass, the angle will be the covering angle will be a lot more than used in the handheld device. Density of people. Okay, I mean density of people. The human detection accuracy depends on the density of people in the area. It can be low, medium, or high. In different types of data situation, the density varies. So the algorithm must be considered to a density factor. Like for example, if you if a camera orientation is a handheld one, so and the density is high, but the problem will be that the algorithm will be scanning few people because of the orientation of the camera. So that's why so everything should be considered before developing an algorithm. Lighting conditions. Of course, when a light reflects on a person, it gets captured in a camera. So lighting affects the vision based detection algorithms. Highlighting can brighten the people, so it might not be detected. It can be considered as some other object, so that's why it gets passed out. And so same goes with the low lighting. The darkness won't be able to detect most of the people around the subject. So people counting algorithm must be robust to low lighting conditions and possible glare. Okay, so we just wrap up by saying this project showcases different algorithms with their accuracy for people as well as address the setback. Out of the algorithms which I've been talking about, yellow and HOD stand out the best among the rest with the best result in every condition. Besides that, this process has mixed reviews by both bystander and blind people regarding accepting the technology. So if if the blind person is going to walking to the streets wearing a camera, the pedestrian besides the person besides the blind person won't be able to know that he is being captured in a real time. So that might be a privacy concern. But as per the survey, it has been said that the people are mostly inclining positively towards the change of technology, because it's benefiting the people who are like less privileges than the people who have more privileges of vision. Future scope. So future scope includes including implementation of this algorithm in real time. This algorithms has been used in already known data set, but now we have to step up and we have to use these algorithms in real time for better results. And addition of exact location of the user and navigation of the user along with detection of the objects on the way can also be added for further convenience and better result. That means if I if I'm a blind person and if I get to know if this person has been standing left to you and this person has been standing right of you, and this person has like northeast northwest, this will give us better information about the surrounding, and the blind person can navigate properly through this properly to the surroundings. Okay, I have used these references, so guys you can go through all these references for your for more information. All right guys, thank you so much for watching.